Okay, today we're talking about Chapter 2, Section 5, Ratios, Rates, and Proportions. All right, so to talk about ratios, right? So we can let's see. Yeah, we'll put that in. All right, let me snip this before I start chit-chatting here. There we go. Alrighty, so a ratio is a comparison of two quantities by division. The ratio of A to B can be written as A over B, or we call it A divided by B, or A colon B, or just simply A to B. Right? That's how uh, that's what we call ratios, or we can write them in any of those ways. And it says attention, the most common notation for ratios is fraction notation, which is this first one. And that is the notation we'll be using in this section, the fraction. So ratios have the following characteristics. Ratios can be reduced just as fractions can be reduced. So we're going to be doing lots of reduction today. The common units in a ratio can be canceled just as factors can be canceled. And generally, ratios are written with whole numbers in the numerator and the denominator, and the fraction is reduced to lowest terms. So we're going to be doing quite a bit of reduction today, but it's not too hard because we've done things like that before. Alright, so example 1, we have an application of a writing ratio. So the floor of a room measures 14 feet long and 10 feet wide. An architect drawing a scale model of the room needs to determine the ratio of the room's length to its width. Write this ratio as a fraction in lowest terms. So we need to write the ratio of the length to the width. Well, we are told that it is 14 feet long and it is 10 feet wide. That is the length over the width. Right? That's it. Except, I mean, to be honest with you, I guess that's the hard part. The hard part's over with. Now we just have to reduce it, right? And 1410 can reduce to 7 halves. And pie charts. I don't know about you guys. When I see pie charts or just any charts, I'm like, ugh, I gotta learn a whole new chart. But it's not so bad. If you just put in the work and just get it over with, you'll feel a lot better about it afterward. And I say that being somebody who was definitely in your seat. I did not go start out going to school for math, but it's just something that I did slowly gravitate towards. It's kind of weird. Anyways, example 2. The circle graph shown here illustrates a monthly budget with categories for food, mortgage payment, utilities, taxes, and other. So use the information from the graph to A, find the ratio of money budgeted for food to money budgeted for taxes. Okay, so looking at A, money budgeted for food is $700. The money budgeted for taxes is $200. Okay, well that's pretty easy. We can reduce that pretty easily, right? Because I mean it's 700 over 200, or just simply 7 halves. Okay, so that's the ratio of money budgeted for food to money budgeted for taxes. Now B requires a little bit more computation, and it's not much more, but it reads, find the ratio of the mortgage payment to the total budget. Okay, so the mortgage payment is $1,200. So we can put $1,200 over, okay, and it says the mortgage payment to the total budget. Well, the total budget is going to be every single one of these added together, okay, including the mortgage payment. So every one of these we're going to add up. So all those added up end up being $4,000. So it's 1,200 over 4,000. Okay, we can reduce that to something like 12 over 40, but we can reduce that even further to 6 over 20, which we can reduce even further to 3 over 10. Okay, and I don't know if you noticed the pattern that I just did there. Um, some of them are really easy, like so 700 over 200, pretty easy, 7 over 2. 1200 over 4,000 is 12 over 40. And then once I got to here, I mean, I could have probably saved a lot more time and just simply divided both of them by 4, but I just cut them in half each time, and I still ended up with 3/10. And I'm assuming that's probably the path that many of you will also take as well, if it's provided for you, if you're able to. All right, so writing ratios in geometry. The lengths of the sides of a triangle are 10 inches, 24 inches, and 26 inches. Okay, so A reads, find the ratio of the length of the longest side to the length of the shortest side. Okay, well, the longest side appears to be 26 inches, and the shortest side appears to be 10 inches. So that's the ratio of the longest side to the shortest side. But of course, we're not done. We need to reduce this, and I'm just going to, again, split them in half. So it would be 13 over 5, and that's it. 13 over 5 does not reduce any further. B, find the ratio of the length of the shortest side to the length of the longest side. Okay, so the shortest side is going to be 10 inches. So the shortest side, yeah. So 10. No, so basically just backwards, right? 10 over 26, and of course that reduces down to 5 over 13, which is basically again just the inverse of A. Okay, so next up, we're going to be talking about rates and unit rates, and we're just going to go ahead and snip the example along with this definition. It's not even much of a definition, just basically the same thing. It's just now we're using different words, right? So a rate is a ratio with different units in the numerator and denominator. The units do not divide out or cancel. For example, if a person walks 20 feet in 8 seconds, the rate is 20 feet in the numerator divided by 8 seconds. And then we can reduce the integer, right, to 5 over 2, so 5 feet per 2 seconds, or in other words, 5 feet per 2 seconds. So we're gonna do that here. So write the following rate as a fraction in lowest terms. So 150 kilometers to 8 gallons of gas. So my rate is 150 kilometers to 8 gallons of gas. Right, and then we can reduce this, divided by 2, so 75 over 4, so 75 kilometers over 4 gallons. And I don't believe 2/3, I don't think that reduces any further. But again, this is just basically the same thing as what we did on the first 3 examples, except now I'm writing, whatever the unit is. In this particular case, it was kilometers per gallon, which is kind of weird because it's what metric over imperial, but that's just the way it is. What is a good one? All right, start from the top. A rate with a 1 in the denominator is called a unit rate. For example, you may attend a concert that costs $20 per person. This is equivalent to $20 a person, or 20 over 1. Other examples of units rates are 70 miles per hour or $52 per month. Right? And of course, note that per means divided by. So when we change changing rates to unit rates, to make a rate a unit rate, divide the numerator and the denominator, so the denominator is 1 unit. Okay, so what does that mean? Well, let's just do an example to find out. So example 5 reads, a bicyclist rides at a steady speed over a level ground of 27 miles in 2.25 hours. Find her speed in miles per hour. So what we need to do is change that 2.25 to a 1. Okay, so what we need to do first, all right, we have 27, and let me fix my screen, it's bouncing a little bit. 27 miles over 2.25 hours. 2.25 hours. Now, we're going to have to get rid of that 2.25, and we can do this in a couple of ways. Well, say a couple ways. Let's just do it the easy way. We can take this 2.25 and then we're just going to divide the denominator by 2.25 and the numerator by 2.25. Okay, well, if we divide the numerator by 2.25, so what is 27 divided by 2.25? It is 12. So we have 12 in the numerator, and we're going to stick with the units, so 12 miles. And then what is 2.25 divided by 2.25? Well, that's just 1. So that's 1 hour. Or in other words, since we now have that 1 in the denominator, we have 12 miles per hour. Right? And that's all we did. We just simply divided the numerator and the denominator by the denominator. Easy peasy. Right, so comparing, can I do, well, I guess I'm about to do this separately. And number 6 is pretty interesting because this is something that I do quite often, and I just did it the other night. Oh, I was buying wings. That's what it was. I was buying wings, and I was trying to figure out what was the better deal. Obviously, for the most part, if you buy in bulk, right, it's going to be a much better deal. And what I mean by buying bulk is, again, for me, if I buy wings, um, the per pound is generally going to be cheaper the higher up. So I got a cheaper rate for $5 per pound. I'm sorry, I got a cheaper rate if I bought 5 pounds than if I bought 1 pound. But anyway, so comparing unit prices, I'm not going to read all that at the top, but I think this is pretty interesting. All right, so in the past, many consumers didn't understand the concept of unit price or know how to determine such a number. Now most states have a law that grocery stores must display the unit price for certain goods they sell. I'm sorry, they must display unit price for certain goods they sell so that consumers can be fully informed. And you do kind of see that. So if you do see a price sticker in the grocery store, look off to the left or the right, depending on the store, I guess. And you're going to see something like 43 cents an ounce or something like that. So grocery stores do indeed provide that, but it says for certain goods, only for certain things do they do that, and I don't really know the criteria for that, but it is true. Anyways, let's jump to example 6. Example 6 reads, a 6-ounce jar of grape jam is priced at $3.99, and a 9.5-ounce jar of jam, of that same jam, is at $2.69. Which is the better buy? All right, now obviously if you are on a budget, you'll probably buy the $2.69 one, right? However, if you're just like, you know what, you know, I have the money, I want to get a better deal so things last a little bit longer. So what you're going to do is you're going to just simply take um, uh, take the ounces and divide it by the money, or how much it costs, right? So we're going to say, we'll start with the first one. We're going to say $3.99, so it would be price per ounce. So it's going to be 3.99 divided by 16. Okay, so what's 3.99 divided by 16? It's about 24.9 cents an ounce. So 24.9 cents um, an ounce. Oh, we'll do. Does it OU? Heck, I done forgot. We'll just do 24.9 for right now. And I guess we just write ounce, right? Yeah, we just write ounce. Anyways, the next one is going to be 2.69 divided by 9.5, 9.5. So that's going to be 2.69, 9.5, and that is 28.3. It's 28.3 cents per ounce. Okay, so obviously buying the more expensive one, I say obviously, it's not actually obvious. Buying the more expensive one, you're going to save per unit. Obviously, you're going to pay more up front, but per unit ounce, you're going to be saving an extra, 3.4 cents. Yeah. Not much of a difference, but it's there. Yeah, see, this is basically what I said. The larger amount units was better buy. Often larger amounts are less expensive because packaging costs less and the manufacturer wants you to buy more of the product. However, the larger amount is not always the better buy because of other considerations such as storage space or the consumer's individual needs. And of course, that last one is a big deal. You could buy a tub of mayonnaise for like $50, but you might not go through it by the time it expires, right? So it does depend on the consumer's individual needs. Oh, well, heck, and the example here is pancake syrup. That's kind of funny. Maybe I should have kept the reading. Okay. Next up is the last part of this section, and that is proportions. Okay, but before we begin that, let's start up here at the top. So special comment on the term per, right? The thing that we just talked about. So be aware that the term per can be interpreted to mean divided by, right? Of course, we are doing a lot of the ratios and stuff. So cents per ounce is just basically cents divided by ounce, which is essentially what we did on the previous example. Dollars per pound, the same thing as dollars divided by pounds, and of course so on and so forth. Okay. All right, and again, like I said, lastly, we're talking about proportions. So a statement that sets two ratios equal to one another is called a proportion. In order for the proportion to be true, the cross product must be equal. Cross products are found by cross multiplying as illustrated here. So if we have 3 over 6 and it's equal to 4 over 8. Okay, so starting out, we can hopefully see that yes, these proportions are indeed equal because 3 6 is half, right? 3 is half of 6 and 4 is half of 8. All right, but what we're going to do is you're just going to cross multiply here. So 3 times 8 is 24. That's good. And 6 times 4 is 24. And that's good. And that's what the cross product is here. All right. Note the different colors. You just cross them. And then that leads us to our definition of proportions. A proportion is a statement that two ratios are equal. In symbols, yeah, in symbols, A over B is equal to C over D, provided that B and D are not equal to 0, is a proportion. A proportion is true if the cross product A times D and B times C are equal. And let's do an example of that to really drive the point home. Okay. We're going to actually go ahead and write this out so I can really demonstrate the cross product here. Let's see, we'll do red 5 over blue, which is 8. That's equal to 7 over 10. Okay. So this problem reads, compare the cross products to determine whether the proportion is true or false. Okay. So we're going to do the cross product here. So we're going to do 5 times 10. Okay. So we're going to say 5 times 10. All right. And that's equal to 8 times 7. Okay, what is 5 times 10? Well, that's 50. And what is 8 times 7? Well, 8 times 7 is 56. And 50 is not equal to 56. Okay, so this is not a true statement at all. Not a true statement, and that proportion is not true as well. And that's it. That's all you have to do is with proportions. It just cross multiply. Now, obviously, there are other ways to go about. Well, let's see. No, let's just there. There's not necessarily other ways to solve. It's just there are other ways uh, to see the cross multiplying here, and that's what we're going to see here with this solving. So solving proportions. Solving proportions are pretty easy. You're just going to cross multiply, and of course, if you have an unknown, you're just going to solve for the unknown. So what do I mean by that? Well, if one of the numbers in a proportion is unknown, it can be replaced with a variable such as x. So for example, we have x over 12 is equal to 2/3. So we're trying to figure out what that x needs to be in order to make it the same proportion as 2/3. Well, you're just going to cross multiply like we did on the previous example, right? You're going to have 3 times x, and then 12 times 2. Well, 3x is simply 3x. 12 times 2 is 24. And if we divide both sides by 3 to isolate the x, we have x is equal to 8. And that's all this is saying here to solve a proportion. And of course, as always, the best way to, in my opinion, the best way to actually see how to do this is to actually see an example in motion. All right. So I'll still color coordinate just kind of so I can stay consistent like I did on the previous example, although we won't make it as thick. So we have 4 over 8. Oh, 4 over 8. And that's equal to 5 over some x. Okay. Well, in order to solve this, right, we're going to say 4 times x, which is equal to 4x, right, which is equal to 8 times 5, right? So this ends up being 4x is equal to 40. And then if we divide both sides by 4, we end up with x is equal to 10. And of course that makes sense, right? Because if we look here, 4/8 is simply, 1/2, right? 4 is half of 8, and then 5 is indeed half of 10. So that's all we have to do to solve proportions. So just simply cross multiply and then solve for x. Right, so same type of problem. We're just going to do the cross multiplying. At least this time, I'm not going to do the color coordination here. So we will, I don't have to. So we're just going to write this as 6 times 24 is equal to 16y. Okay, well, 6 times 24, or 6 times 10 is 60, times another 10 is 120, and then times 4 is 24, so 144. So we have 144 is equal to 16y, and we're going to divide both sides by 16. So we end up with 16 goes into 9 is equal to y. And then applications, and always go to applications because we have to see, how this kind of translates into a real world problem here. I'm pretty sure this might be the last example. I'm going to look just for my sanity's sake. Yeah, just one more. Alrighty, so applications. Problems that involve two ratios are the type that can be solved using proportions. So when we need to solve an application using proportion, kind of the same procedure as before. We're just going to identify the unknown quantity and use a variable to represent this quantity. We're going to set up that proportion, and then we're just going to solve the proportion. So looking at example 10, solving proportions. A motorcycle will travel 352 miles on 11 gallons of gas. How many miles will the motorcycle travel on 15 gallons of gas? So we're going to do miles per gallon, right? We'll travel 352 miles on 11 gallons of gas. So one proportion is going to be 352 divided by 11, and that's equal to how many miles will this motorcycle travel on 15 gallons of gas? So we're going to say, so 15 is the gallons, right? And we don't know the x. So we have to solve for x, right? Well, 352 times 15, I feel like doing this one in my head, 352 times 15 is 5280. So we say 5280. Again, we're just cross multiplying here, like so. Right, what I said, 5280. I think that's how many feet are in a mile. Maybe not. I don't know. 5280 is equal to 11 times x, which is simply 11x. All right, we're going to divide this by 11. We get 480. Okay, so we have 480 is equal to x. So on 15 miles, I'm sorry, on 15 gallons of gas, our motorcycle can travel 480 miles. That's pretty darn good, I think. I don't know. I don't know motorcycles miles per gallon. I don't own a motorcycle. I just know that I would love to get um, 480 miles of 15 gallons of gas. Right. And then lastly, we have a an architect here. So an architect draws the plans for a building by using a scale of half inch to represent 10 feet. How many feet are represented by 6 inches? Okay, so how do we set up this particular um, ratio? Okay, so what we're going to do is we're going to say, all right, so he has a scale of half inch to represent 10 feet. So, half inch to represent 10 feet. Okay, so we're going to do this like this. Uh, we're gonna have some unknown number being, so we're gonna say half inch to represent 10 feet. How many feet are represented by 6 inches? Okay, so we're gonna say half inch over 6. That's gonna be equal to 10 feet over y feet. Okay, so what we did here is we put inches on the left, so it's kind of it's like this. It's inches. Let's try it again. Inches, inches, and then feet, feet. Okay, so this is a proportion that we're going to set up, and we're again just going to simply cross multiply here. So we're going to end up with 1/2 y is equal to 10 times 6, which is 60, and and multiplying both sides by 2 here, right? Because I have a 1/2 on the left. So if I multiply both sides by 2, then we'll just go ahead and write that out. So 2, they cancel, and then times 2 over here. So we end up with y is equal to 120. Okay, so 6 inches represents 120 feet. Right? That was a little tricky. I had to pause for a moment, but that's that, and that concludes today's lecture on 2.5.